for the final 2 weeks of our course here this summer, we're going to use kind of everything we've learned to bring it all together to what's called vector calculus. So we're going to be looking at, so we take some of the vector stuff that we learned at the beginning of the semester, and then we take our knowledge of partial derivatives and multivariable differentiation. So we kind of have vectors, partial derivatives, and multiple integration. And you kind of combine all these together, and plus some other stuff, of course, physics too, a lot of physics and the applied settings, you get vector calculus. And so what we're going to be doing is taking a look at some of the first topics of vector calculus that you will discover after you have the proper notice to get a good grip on vector calculus. There's obviously a lot of math leading up to this that you need, right? Vectors, partial derivatives, multiple integration. There's a pretty decent background of math and calculus that you need to know to get to this point. And so now we're finally equipped to be able to talk about this topic a little bit, which I personally find very interesting. And to do this, what we're going to start with talking about is vector fields. Vector fields are the kind of the foundation for which you build vector calculus off of. And whoops. It's important that we really understand vector fields before we get into vector calculus, because a lot of the underlying math and structure is vectors, obviously. So let's get a good idea of what vector fields are. And I want to start with just an example. Or maybe not even an example. Let's call it motivation. All right, let's get some motivation for why we want to talk about vector fields. So let's imagine we want to model the velocity of water particles on the surface of a river. Okay, and so let's use blue. Say here's the river. Okay, and we have water running down this river, right? And we want to model the velocity of the water particles. Well, we know velocity can be represented as a vector, right? Because velocity has both direction and magnitude. That's why, like, our convention is that if your object is moving into the positive x direction, we say it has positive velocity, or if it's moving in the negative x direction, it has negative velocity, right? Speed, however, is just the magnitude. We don't care about what direction we're traveling in. We just care how fast we're going. Now, velocity, what we care about is how fast we're going and what direction we're moving. And so you can think about taking, maybe I'll draw them in green here. You have a bunch of water particles down this river, right? Obviously way more than what I'm drawing. And at any given time, you want to pick, say you pick a particle that you observe and you want to calculate its velocity. Well, once you calculate its velocity, you can assign an arrow describing the length of the arrow describes the magnitude at which the particle is traveling, and the direction tells you what direction the particle is traveling, right? And so maybe this part back here, you can imagine maybe the ground underneath and around this river is really sloped, right? And so water is moving really fast. And so the vectors associated to these points are much bigger, right? Because we know the length of an arrow is important because it tells us the magnitude, right? Where shorter arrows indicate smaller magnitude. And so what shorter arrows would indicate in this setting is lower velocity. And so say here it kind of has to almost, the ground either levels out or it actually has to climb just a touch, right? And so you could start to get maybe your particles slow down at this part of the river. And so your velocity vectors here are smaller. And you can do this at every point along this river. And this whole family of vectors here that are indicating velocity of these water particles, this collection of vectors is what we'll call a vector field. This entire picture of all these vectors, this would be the velocity vector field. Okay, so this is kind of the idea. And you can see now that like vector fields appear everywhere. If you want to map like the gravitational force that one like celestial body exerts on another, you can indicate this with vectors, because gravity is a force that has both direction and magnitude, right? Gravity pulls harder in other places of the universe, like depending on, like the sun's gravity is much more than the Earth's gravity, right? And so your proximity to the sun determines how much the gravity is affecting you. And so you can model position, velocity, acceleration via vector fields. You can model gravitational force. You can model magnetic fields. A lot of electromagnetism settings are to be modeled with vector fields. And so definitely in physics, velocity or vector fields are very important, right? And so let's give a formal definition now and start to see some examples. So a vector field and we'll indicate this F here, capital F, in R2. And so I'm going to, in parentheses, I'm going to give the definition for the three-dimensional case as well, right? And then you could extend this to an arbitrary dimension if you'd like. And so, or I'll say or R3 is an assignment. So it's a function. You can think of a vector field as a function, right? Because that's what it is. It's a vector valued function. Is an assignment of a two-dimensional So again, I want to also give the definition for the three-dimensional case at the same time. So I'll say or 3D vector. So it's an assignment of a vector to each point, and we'll call this vector f of xy. So this will be the assignment of the two-dimensional or three-dimensional f of xyz vector to each point x and y. That's going to be an element of some domain, which will be like in the two-dimensional case, it'll be a subset of R2, right? In the three-dimensional case, or it would be x, y, z is contained in some domain, is an element of some domain that's a subset of three-dimensional space, right? And then here we say D is the domain of F. Okay. And so this is what a vector field does. A vector field, I'll draw like the 2D picture here, and then the 3D picture here. So x, y, z, x, y. What a vector field does, say we have a vector field f of x, y, it assigns a vector to each point. So you pick a point, x, y, you plug that point in to the vector field and it spits out some vector. And you do that for every single point, right? So there's obviously a lot of points in space, and to each point you get some vector, right? And then you see why it's called a vector field is because once you kind of look at a picture with a lot of the vectors drawn, you know, it really is a vector field. It's like a field of vectors, right? And so the ideas are analogous between all of the dimensions. It's just there's more dimensions, right? So you pick a point x, y, z, and then there's some vector in 3D space, right? And so you, based on some vector field, let's say this one's like f of x, y, z, you know, then you have all these vectors doing whatever, right? It depends on the expression that's given for the function, right? And how do you know what the vector field is going to look like? Well, you have to plot points, right? You'll have to plot a bunch of points to get like samples for what this starts to look like. And you'll know, or what you plot points to is kind of the vector representation of these vector fields, right? And so here's some notation. In like the two-dimensional case, so we have f of x, y, this vector field is where the x and y entries can be functions, like scalar functions, right? Not vector valued functions. They'll be scalar functions. So we have like p of xy and q of xy, right? Or you can express this as p of xy I hat plus q of xy j hat. Okay, and so now the components of your vector are functions, and they're telling you at the point xy, this is the vector. It's going to be p I hat q j hat, right? And so in 3D, we have something very similar. We just have one more component to keep track of. So this would be like p of xyz, q of xyz, and then maybe in the z component, we have some function of 3 variables. We'll say r of xyz. And again, you know, you could express this as, maybe I'll just write it in shorthand. This would be like p I hat plus q j hat plus r k hat. But again, p, q, and r are all functions of 3 variables here. And so this is how you will determine what your vector field looks like. You'll pick a point, right? You'll pick some point, then you'll plug it in. And you'll get some number when you plug in, right? You'll get a number for each component, which gives you the vector, right? And so like if you plug in the point x naught, y naught, then your answer, like that will be just one vector, right? Not a function. This is a function telling you at every point what the vector is going to be. So the most beneficial thing with vector fields starting out, the most beneficial thing you can do is look at different examples. And that's true with most mathematics, right? Is you learn the definitions, but then it's, okay, let's see some examples. Let's see what's actually going on here while using the definition. So let's look at some examples. So here's the first one. Let's sketch the vector field f of xy equals x over 2 I hat plus y over 2 j hat, right? And so you can see this is a function here, right? Now our p of xy is x over 2, and this was our p of xy. And then our q of xy is y over 2. And we want to observe we want to give a sketch of this vector field, right? And so this sketch should be a family of vectors. And what I always like to do to get an idea for sketching vector fields is start by plugging in points. And so let's look at f of 0, 0, right? Well, if we plug in f of 0, 0, that's 0 over 2, comma 0 over 2. So that's the vector 0, 0, which is a point. So at the origin, there is the vector is just the trivial vector. It's just a point, right? So let's look at, well, let's look at like 1, 0, right? We can maybe just go with some simple points to start here. F of 1, 0 is going to be 1/2, comma 0, right? And so at the point 1, 0, we have a vector with the x component 1/2, the y component 0. And so if this is like 1, 2, 3, et cetera, this is a vector of length 1/2, right? So we get something like this. And then we can pick another point. Let's say f of 1, 1. Well, this is going to be the vector 1/2, 1/2. And so 1, 2, 3, let me extend. So at the point 1, 1, we have a vector given by 1/2, comma 1/2. So we get something like this, right? Because you'll have to look at the magnitude as well, like, or, you know, just based on components, this is over 1/2 unit up 1/2 unit, right? And so we can keep going. What I usually like to do is I pick the origin, and then I pick kind of like points around a rectangle, right? So here, I'm going to pick like 0, 1. This would be 0, 1/2, right? So here I'm going to have 0, 1/2. So we get something like this. And then if I pick like, you know, this point over here, again, I would be going around kind of a rectangle with sides 1 unit away from the coordinate axes, right? And so I kind of just pick like major points along these. Obviously, you can pick whatever points you want. These are always convenient. And then, you know, if I don't get a good enough idea from here, then I'd go out to like a box 2 units away. And then you can look at points on that rectangle as well, right? And then you just keep kind of going until you get an idea of what all these vectors are doing. And so let's pick the point -1, 1. And this is going to be the vector -1/2, 1/2. So I'll get, looks like this vector here. And then let's keep going. So this point is f of, looks like it's going to be -1, 0, which is -1/2, 0. And so one thing I've noticed is that these all point away from the origin, right? And let's do 3 more just to get an idea of these bottom 3 here. Let's do f of the point -1, -1. This is going to be -1/2, comma -1/2. So we'll get this. And you can see if we plug in f of, so this point here will be 0, -1. We're going to get 0, -1/2, right? So we get something like this. And then lastly, we'll have f of 1, -1, which is 1/2, -1/2. So we move to the right half unit and then down half unit. So we get this vector here. Okay. And then notice, what will you get if you plug in like points like 2, 0, 2, 2, 0, 2, all of these points, right? Well, then it's just going to be like the same vectors, but scaled, right? It'll be doubled, right? And so if you move out 1, you'll just get like double the length with all these. And this is an example of a radial vector field. So this is a radial vector field. Okay. It's called a radial vector field because in any given direction, all vectors are pointing out, like radially outward here. You can have radially outward vector fields and radially inward vector fields, right? This is an example of a radially out vector field. And so, you know, what you would get is that along a given circle, you know, the farther out you get, the larger the vectors get, because your X and Y values are getting larger in magnitude, right? And so you can see this is what the vector field X over 2 I hat, Y over 2 J hat looks like. And again, there are examples of radially inward vector fields, right? And so as you get to the origin here, the vectors are going to get really small because the X and Y values are going to be really small. And then once you're actually at the origin, your vector is just a point, right? So there are also radially inward vector fields. Like you could have something where they're all pointing inward like this, right? So, and you'll see examples of that on the homework. Let's look at another example. Let's look at the vector field f of xy equals y comma negative x. Let's see what this vector field looks like. So again, we'll get our coordinate axes for our sketch here. And let's pick some more points. Let's look at f of 0, 0. Again, I find it helpful to go around points like this and like kind of again on like rectangles that are integer units away from the x and y axis. So if I pick 0, 0, well, you can see I'll get 0, 0. So this is the origin again. If I pick f of 1, 0, I'm going to get, well, so the y component, so the variable y is in the x component. So they're kind of flipped, and then the y component is negative x, though. So this is going to be 0, negative 1. And so this is, let me give myself some ticks here to indicate what one unit is going to be. And so this is 0, negative 1. So I'm only moving down 1 in the y direction, right? This was the point 1, 0. Let's look at the point 1, 1. Well, then I'll get 1, negative 1, right? And so this is, the base point is 1, 1. I'm moving 1 unit to the right and 1 unit down. So I get something like this here. And then let's pick f of 0, 1. Sorry, those should be rounded. Equals, well, the point 0, 1 is going to be 1, 0. So at the point 0, 1, we have the vector 1, 0, which looks like this. Kind of matches up with that terminal point, right? F of, let's look at negative 1, 1. This is going to be the vector, well, y is 1, so the x component's 1, and then negative, negative 1, so this is 1, 1, which will be this vector here, right? 1 unit to the right, 1 unit up. Hopefully this isn't too difficult, right? Because all we're doing is plugging in points and examining what the resulting vector is, and then we plot that vector, right? Based on whatever point we plugged in gave us. So here the point would be negative 1, 0, which will give us 0, 1, right? So that's up. We can pick, again, you know, when we're first learning vector fields, it's important to pick like a lot of points so you can really get the idea of what's going on here. So this is the point -1, -1, which is -1, comma, +1. So we're going 1 unit to the left and then up 1 unit. So something like this. And then let's finish off with a few points. So here, let's plug in this point. F of this would be the point 0, -1. Right? And so if we plug in 0, -1, we will get -1, 0. So this is pointing to the left, 1 unit. And then the last point we can pick is, that's the point 1, -1, which will give us the vector -1, -1, right? And so we're to the left 1 unit and down 1 unit. And so what you can see is if you follow the tips of these vectors, it kind of traces out like a circle, right? It's like a rotating vector field here. And if you notice, if you plug in, if you go through the points like 2, 0, 2, 2, 0, 2, -2, 2, you're going to get that they're all the same direction, but of greater magnitude. So the farther out you are, the longer the vectors, right? And so this is an example of like a rotational vector field, right? Rotational vector fields are very good for modeling hurricanes, right? Wind speeds of a hurricane, because the eye of the storm in a hurricane, it's very calm. The winds are very low, and it's very not a hurricane, right? It's not a storm. But as you move to the edge of the hurricane, that's when the wind speeds get really high and really violent, right? And so this would be a good model, or these kinds of vector fields are very good for modeling like a hurricane or a tornado or a cyclone or some sort of rotational storm, right? Let's look at a 3D example now. We've looked at two-dimensional examples. Let's look at one 3D example. So let's look at f of x, y, z is the vector field 1, 1, z. Okay, and so now we have three-dimensional space, x, y, z here. Okay, and we want to look at some vector field, right? Well, again, we pick points. So what is the point? Let's start with the origin, 0, 0, 0, right? Well, that's going to be the vector 1, 1, 0. And so the resulting vector is only in the xy plane, right? And so it's 1 unit up, 1 unit to the right. And so we'll get this here. And if you notice, the xy plane is when z equals 0. So any point you pick in the xy plane, it's just a copy of this vector, right? So the entire xy plane is just these vectors, like parallel copies of these vectors. Right? And so you can kind of picture that all being contained to the xy plane here. And then you'll go up, right? Here, this particular vector field is quite nice to picture what's going on, right? Because, well, then you can look at when z equals 1, right? And so you'd have points like f of x, y, 1. Well, these would just be all vectors 1, 1, 1. And so when you're up 1 unit, right, say this is at this green plane is at the level z equals 1 here, well, then you're going to have vectors 1, 1, 1. And so they'll look, the projection to planes parallel to the xy plane will look just like they do in the xy plane, but now they're raised 1 unit. So vectors on this, we go out 1 unit, over 1 unit, and up 1 unit. And so vectors will look like this, right? Well, they'll actually be going up 1 unit as well as over and out. And so you can see if you get up to the level like z equals 2, then they'll still be, z equals 2, f of x, y, 2. Well, this is the vector 1, 1, 2. And so the x and y components are unchanged, but now it's just taller, right? Now they're just 2 units tall. And so you can get an idea here of, the higher your z value goes, the more these vectors, they're not going to change how far out they go in the x and y directions, but it is going to change how far up they're pointing, right? And then when you go to negative z values, it'll be how far down they're pointing. So if you were to look all the way down at like z equals -1, see if I can draw it, like, imagine that being like way under, not way under, but 1 unit under, right? Well, then it would be 1, 1, -1. And so they'd all be down. They'd be going down 1 unit, right? And so a 3-dimensional vector field is a little harder to picture. They look beautiful in computer programs. Like if you code or like go to some online vector field grapher, you can type in 3-dimensional vector fields and they look very pretty and it's very clear what's going on, right? My chicken scratch drawing is a little less clear, but hopefully you still get the idea and you can see what this vector field would look like. It's like as you take some plane and you go up, the vectors kind of grow, right? They're kind of standing. And as you go down, the vectors are kind of, they're swinging, they're lowering, right? They're angling downward. For the next example, I would like to give a definition first. So a definition here is a vector field. We'll call it F with all f of x, y, or in 3D, f of x, y, z, right? With all f of x, y unit vectors, we call F a unit vector field. Pretty intuitive. So if every single vector in your vector field is of length 1, then we call it a unit vector field. Okay, so let's look at an example. We saw this rotational vector field here given by f of x, y equals y negative x. And as you moved out, right, as you moved away from the origin, the vectors got larger and larger and larger, right? Well, now we can look at the unit vector field, f of x, y equals y over root x squared plus y squared, and negative x over root x squared plus y squared. Okay, and so you can see here, well, let's first verify that this is a unit vector field. Let's take the magnitude of f. It's going to be the square root of y over root x squared plus y squared, that whole thing squared, plus negative x over root x squared plus y squared, that whole thing squared, right? Whoops. We can simplify this. I notice that they both will have a common denominator of x squared plus y squared, right? Because it's root x squared plus y squared. And once you square that, the root cancels with the outermost square. And then so we just have to square the numerators and add them up. And so we'll have y squared plus negative x squared, which is positive x squared, right? and these expressions are the same, so we get root 1, which is 1. So indeed, this is a unit vector field. That's good to check. So how did we go from a like comparing these vector fields, how did we go from a non-unit vector field to a unit vector field, right? And here you can see the directions are all the same, right? The directions will remain unchanged. It's just the magnitudes have been fixed now to a length 1. So if you were to look at f of xy here, you would see that if you pick a circle, right, of a given radius, well, the first time, all of these vectors, as you picked bigger radii, the vectors got bigger. But now, this unit vector field, they're all of length 1, no matter how far or close to the origin you get, right? So these are all length 1. And you won't be gaining magnitude as your distance from the origin increases, right? And so you can kind of imagine that it's just these like spirals, or not spirals, it's just these circles of vectors of length 1. And what did we do to go from that kind of the non-unit vector field to the unit vector field? Well, let's look back at what f of xy was originally, right? This was y negative x. What was the magnitude of this, right? The magnitude of this f was, well, that's root y squared plus negative x squared, which is root x squared plus y squared. And so we know we can find unit vectors by dividing by the magnitude. And that's exactly how you get a corresponding unit vector field out of an arbitrary vector field. Notice we divided by the magnitude of the vector field. And that's how we got this corresponding unit vector field, where all the directions of the vectors are the same, but now all the magnitudes have been scaled to be precisely of length 1. And so we can make a remark here that if, and so I'll write this in the 3D case, right? It's true for 2D case as we've seen right here. If we have the vector field f equals like p, q, and r, remember these are all functions, is a vector field, then the corresponding unit vector field, maybe I'll call it like f sub u for like a unit vector field, is the vector field p over the magnitude of f in the first component, q over the magnitude of f in the second component, and then r over the magnitude of f in the third component. So you see, to get a unit vector field, it's very intuitive based on how we got unit vectors, right? Because these are all just vectors still. So you can get a unit vector field by dividing each component by the magnitude. This process here, this process of dividing through by the magnitude is called normalizing. A vector field. Or, you know, we can say this process is called normalizing the vector field f, okay? And so if I ever say, I won't use this notation very much, but it's still important to, or excuse me, I won't use this terminology very much, but it's still important to define it, because sometimes I may say, you know, you need to normalize the vector field, or we're going to normalize the vector field. And what that means is I'm just making it, I'm finding the corresponding unit vector field by scaling these vectors by 1 over the magnitude. Okay, so we've seen a handful of examples now. Let me give, what I'd like to do is give a definition, a few theorems, and a few examples, and then this will wrap up our discussion of vector fields. So this video might end up being a little long, and I apologize. This, what's left to discuss is not enough to constitute an entire new video. So let's just wrap up our discussion on vector fields while we're here. So I'd like to give a definition. A vector field, say F, is a gradient, more commonly called a conservative vector field. If there exists some scalar function, so let's say if there exists a scalar function meaning you input numbers and the function spits out numbers, right? There's functions that we're used to, like y equals f of x. If there exists a scalar function f such that our vector field, capital F, is equal to the gradient of our scalar function, right? And in this case, we say f, lowercase f, is a potential function. For vector field f, okay? And so gradient vector fields, or probably from now on, I'll call them conservative vector fields, are very important topics. And in fact, this is from, after this section, we will talk about line integrals, because now that we have a definition of vector fields, we can talk about scalar and line integrals and vector line integrals. So we'll define that. But then after that, we're going to spend an entire one, maybe even 2 lecture videos on conservative vector fields. They play a very big role in vector calculus. So let's see an example of a conservative vector field, right? So it's a conservative vector field if it's the gradient of some function, basically. Is a gradient vector field or a conservative vector field is a vector field such that it's the gradient of some function f. So let's look at an example here. Let's verify that the function f of x, y, z, which is x squared y, z minus sine of x, y, let's verify that this function is a potential function for the following vector field. F of x, y, z equals 2xyz minus y cosine xy, comma, x squared z minus x cosine xy. And then in the z component, I ran out of room, but we'll just have x squared y. And so what does it mean to verify that f is a potential function for this given vector field? Well, it means we need to show that the gradient of f is equal to this vector field, right? And moreover, what we need to show is that f of x, y, z, so again, this is need to show this, which more explicitly stated is that this is partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z, right? This is what we want to show right here. This is what it means for f to be the gradient of some function, right? And so let's take let me copy the function down here, and then we can take our partial derivatives. So we have x squared yz minus sine x y. So let's take the partial derivative with respect to x. Well, y and z are constant, so this first term is going to be 2xyz, and then the derivative of the second term, well, the derivative of sine is cosine, so cosine xy, but then it's times the derivative of the inside with respect to x, right? And y is a constant, and the derivative of a constant times x with respect to x is that constant. And so we see this is our partial derivative with respect to x. Now, let's compare. We have 2xyz minus y cosine xy. Let's look at what this was. 2xyz minus y cosine xy. Awesome. So we're good for the x component. Let's take the partial derivative with respect to y. Well, x and z are now constant. This is y to the first power, and so the derivative of all those constants times y with respect to y is just those constants. So we get x squared z, and then minus, we'll have something similar here. The derivative of sine is cosine of xy, but now it's times the derivative of the interior with respect to y, and so we'll get an x here. And so let's check that the second component of our potential function, or excuse me, of our vector field, is x squared z minus x cosine y. So we have x squared z minus x cosine xy. Boom. So that means the x and y components are good. Now let's just take the derivative with respect to z. So df dz equals, so the derivative of the first piece will be x squared y, and then the entire term is constant with respect to z, or the entire second term is constant with respect to z. So the derivative of that is 0. And we have df dz is x squared y. And let's check. Yes, our z component for this vector field is x squared y. And so now this is indeed, this vector field f is the gradient of this function. And therefore, we say that f is a conservative vector field with potential function given by f up here. So there are two theorems I would like to give about conservative vector fields. The first one is about the uniqueness of potential functions. Okay, so let's assume that f is a conservative vector field. I'll just write VF for vector field. So let's assume that f is a conservative vector field such that f is the same as the gradient of f, and it's also the same as the gradient of g. So we're assuming that there are two potential functions here. Then f is the same as g, but differs by a constant. So for some constant c, right? And this makes sense because if their gradients are the same, well, then they have to be the same up to a constant, right? Because the constant wouldn't show up. Like if you were to try to go backwards, right? What if we were try to do that? What if we were trying to go from a gradient backwards to a multivariable function, right? Well, we'll see how to do that in the section that we talk about conservative vector fields. There's actually a kind of a nice paradigm and process you can follow to do that. But intuitively, it makes sense that, well, if their gradients are the same, then these functions can only differ by a constant, right? All of the variables themselves should be the same. And that makes sense. So the next theorem I would like to state is called the cross partials property. And when we do learn about how to go from a gradient, like say all you know is a gradient, right? You don't even know what the function f is. When we do learn how to recover the function from just the gradient, we will use this cross partials property. But first, let's just state what this is. So here's the 2D version of the theorem. Let's imagine we have f of xy is p of xy, comma, q of xy. Let's say this is a conservative vector field. Then the property is satisfied that the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x, right? And why is this called the cross partials property? Well, if you set up, like, you know, here's the variable x, here's the variable y, you know, you can set up like a table where here's the component, right? Or so, let me do this the other way. Here's the component. Here's the variable. So like the first component is p of xy. The second component is q of xy. Well, what's the first variable? It's f of xy, right? So x, y. And the partial derivative of p with respect to y, so this is del p del y, is the same as the partial derivative of x, or partial derivative of q with respect to x. And so just as kind of like a nice mnemonic device, you see this cross that's made here, right? And so we call this the cross partials property. So what that means is, if we think about the logic of this statement, that says if f of xy is conservative, then the cross partials property is satisfied. Logically, what is the converse of this statement? So if we had something like A implies B, this is the same as not B implies not A, right? And so what that means is if statement A is if f of xy is conservative. This is statement A. What's statement B? Statement B is that dp or del p del y is del q del x. This is statement B, right? So the logic here is that if A implies B is the same as not B implies not A. So what does not B mean, right? Well, not B would mean del P del Y is not del Q del X. This implies that F, what is not A? Not A would be that F is not conservative, implies F is not conservative. And we will use this version of this theorem to prove that vector fields are not conservative. If you're just given a random vector field, you may not know if a function f even exists such that it's the gradient, right? Not all vector fields are conservative. So we can figure out if a vector field is not conservative by seeing if the cross partials condition fails. If it fails for a given vector field, then the vector field's not conservative. However, if it is satisfied, right, then we should look for a potential function, right? So we'll use, again, kind of the converse of this statement to prove that certain vector fields are not conservative, right? And so let me state the 3D case as well, because it's different for the 3D case. This is the 3D case. If F is, let's call it PQR, if this is conservative, then we have the cross parcels condition now is, so again, this is cross parcels property. We'll have del P del Y is the same as del Q del X. So this is the same as the 2D case, but now we also have that del Q del Z is the same as del R del Y, and we also have that dr del R del X is del P del Z. And so again, if you list these like in the order, P, Q, R, and then the variables X, Y, Z, you see the first cross parcels condition is that del P del Y equals del Q del X. The second one is that del Q del Z equals dr dy. And then the third one is that dr dx equals dp dz. And so you get this kind of picture. Now in 3D, there's 3 cross parcels that are satisfied, right? And so again, the converse logically means that if any of, let's label these like equation A, equation B, and equation C, right? Each one for each equality here. If any of A, B, and C fail, that implies the 3-dimensional vector field f of x, y, z is not conservative. Okay, and so let's quickly look at some examples by using these altered versions of the theorem to show that some vector fields aren't conservative. We'll do a 2D example and a 3D example. Let's do an example here. Let's show F. So let's show that F is not conservative. Okay, so let's look at F of xy was our kind of rotational vector field from earlier, y negative x, right? And so what do we need to calculate? Well, let's go back to our revised version, or not revised, but our altered version of this statement of the theorem in 2 dimensions, right? If these cross parcels are not the same, then f is not conservative. So we need to calculate partial derivative of p with respect to y, partial derivative of q with respect to x. Partial derivative of p with respect to y is 1. Partial derivative of q with respect to x is -1, and these are not equal. So this implies that f is not conservative. Right? And what is this, moreover, what does this imply? That means there does not exist. So there does not exist. So remember symbols here. This backwards E means there exists. So an E with a slash through it means there does not exist. Okay? So this means there does not exist an F such that the gradient of f equals this vector field. Okay, and so let's do a 3D example. Again, let's show that this isn't conservative. F of x, y, z equals 7 negative 2 x cubed. So remember, for the cross parcels in 3D, we need to show that if any of A, B, and C fail, then f is not conservative. So let's look here. Let's start with dp, dy, and dq, dx. So dp, dy is 0 because that's constant, and dq, dx is also 0. So that one's fine. What is b? B is dq, dz, dr, dy. dq, dz is, well, so remember this is p, q, r, right? Here. Just so we can keep that in mind. Well, dq, dz is 0. What's dy, dr? Well, that's also 0 because there's no y in the third component. So that one's fine. What about the last one? The last one is dr, dx, dp, dz. So dr, dx is 3x squared. However, dp, dz is 0. And these are not equal to 0 when x is non-zero. And certainly, we can have non-zero x values, right? Non-zero x values are in the domain of this vector field. And so this did not work, which tells me f is not conservative, which means that f votes Democrat. Okay, so this wraps up what I wanted to discuss about vector fields. Again, I apologize, this video got a little lengthy. I think it was not enough to put into 2 videos, but maybe a little too much for 1 video. So I apologize for the lengthy video here. Again, now that we have a nice background of line integrals, or now that we have a nice background of vector fields, we will discuss line integrals, and we'll talk about scalar line integrals and vector line integrals. So this is kind of the foundation for the rest of our discussions on vector calculus.